Yes, welcome back guys on India's largest e-learning platform, that is BYJU'S Exam Prep. So today we are going to start this wonderful crash course, and that is going to help you in GATE 2022 exam. And guys, in this crash course we are going to discuss some wonderful topics which are either very important or very difficult. So guys, these are really going to help you to score well, to achieve your dream. So please tell me, am I properly audible and visible to all of you or not? Yes, G1, Pradyumn, good afternoon guys. So kindly share this session in all the Telegram and WhatsApp groups so that other students can also join. Jinil, hello dear. Krishnakant, good afternoon. Yes, wonderful guys. Okay, so guys, this session is going to be very important, and today we are going to discuss StressStrain Diagram, which is really very important topic, and this is the topic which every student is not knowing it completely, and nowadays very difficult questions are being asked from this. Okay, dear, it will be for 2 months. It is a 2-month crash course. Okay, Suraj, only sir ये class का PDF, dear, आपको all Telegram channels में ये PDF मिल जाएगा. Okay, so don't worry about that. Okay Jinil, I will surely do, don't worry, I will surely do. परविंदर नमस्कार. साम्यक, yes, good afternoon. PDF आपको सभी टेलीग्राम चैनल्स पर मिल जाएगा. फ्रेंड्स फॉरएवर, गुड आफ्टरनून डियर. ओके, सो गाइस, नाउ वी आर स्टार्टिंग द सेशन. So today's topic is StressStrain Diagram, and guys, if you see from last 3 to 4 years, the questions is coming every year from this topic, and that is beyond the level of thinking of the student, because they are asking the question from the elastic recovery. So my dear, this is even important for production part as well, because in metal forming also you are having the question which are from this topic. So my dear, you are going to get help in both the subjects from this topic. Yes, Manas, good afternoon. Sumit Shoran, yes, champion study plan will continue, don't worry. This is extra thing guys, this is extra thing, this is an extra thing. Yes, Bhavesh, namaskar dear. Okay, so guys, this is some detail about me, and today's subject is strength of materials. So guys, now we are going to start. First of all, as you know that when we are talking about the StressStrain diagram, my dear, StressStrain diagram we are getting from a wonderful test that is named as tension test. My dear, like you have seen the tension test, similarly there are many other tests in the strength of material, that is compression test, shear test, torsion test. Yes. हाँ dear, production भी पढ़ाऊंगा, don't worry. Production I will be taking in crash course, don't worry. So my dear, now we are talking about the tension test, because in strength of material this tension test is going to be performed on universal testing machine. And my dear, when we are talking about this tension test, my dear, this is a test which can give you 19 elastic properties. So my dear, this is the test which gives you the 19 elastic properties. My dear, when we are talking about the 19 elastic properties, it includes the properties like Young's modulus, it includes the properties like yield strength, it includes the property like ultimate strength, and like ductility, and like toughness, and like resilience. These are the properties you are going to get. And guys, yes, in this crash course we are going to discuss theory as well as numerical both. Okay, so first we will study theory for first 40-45 minutes, then in last 10-15 minutes we will be going for the numericals. Okay, so my dear, when we are, and numericals will be other than GATE, I am telling you that. Okay, so my dear, when we are talking about this on universal testing machine, 19 elastic properties you are going to get. Actually, I will be showing you the test specimen, but in general the test specimen is having dog bone type of shape. So my dear, this is the dog bone type of shape which is there with the specimen. And my dear, you can see this is the universal testing machine. This is holding this specimen like this in the jaws, and they are going to apply the tensile forces like this. You can see this is how this specimen looks like. This is how this specimen looks like. You can see that. Okay, so before testing, this is the case. This is before testing. And my dear, when the fracture is going to take place, this is after the fracture. Okay, this is after test. So my dear, both the diagram you can see, when you will be applying the tensile loading, obviously the length of the specimen is going to increase. Asutosh Mishra, yes, good afternoon dear. कई दिनों बाद आप आए. So how's your preparation going on? Is it fine or not? Yes, Mahadev, good afternoon dear. So my dear, this is what is the exact diagram. So we are going to apply the force onto this diagram, sorry, onto this figure, this specimen. So my dear, the length under consideration of this specimen is this one, and this is also said to be the gauge length. So my dear, this is the length under consideration, and it is also said to be the gauge length. It is also said to be the gauge length. Guys, today I would like to tell you wonderful things which you have never seen before. So don't miss the session, okay, and like and share the session with others as well. So my dear, this is the gauge length on which we are going to have the consideration. हम सिर्फ इसी पार्ट के ऊपर अपनी नजरें गड़ाए हुए हैं कि what is going to happen in this part when you are going to apply the forces. This part is just for the purpose so that jaws can hold it, okay. So when they will be applying the force, my dear, initially the diagram which was proposed, that diagram was the diagram between force and deformation. So initially we were having the P delta diagram. So my dear, when we were making the P delta diagram, there was a problem. Yes, Manas, good afternoon. What was the problem? Actually, you know, when you derive the expression for delta, you get delta to be equals to PL upon AE. So my dear, let us say if you have a specimen with area A, okay, and you are having some curve like this, let us say. Then after some days you are going to perform a test on a specimen with area 2A. Then my dear, when the area will become 2 times for the same deformation, load should also be double. So the curve will be just taking a jump like this. So for this area, this is the curve. For this area, this is the curve. So for the same deformation, this is for area A, this is for area 2A. So you can see when the dimensions will be changing, you will be having the change in curve. So we wanted to make it independent of the dimensions, guys, because otherwise whenever the dimensions will be changing, we will be having this kind of things. So my dear, we wanted to avoid that. We don't want it different curves for changing the dimensions only, for changing the length only. So to avoid all these things, my dear, what was the things proposed? It was proposed to replace the force by a quantity known as engineering stress. That is nothing but force but a original area of cross section. Original area is the area in the starting of experiment. And my dear, then delta was replaced by delta upon L, that is nothing but engineering strain. So my dear, load was replaced by engineering stress, deformation was replaced by engineering strain. So my dear, when it was replaced, the diagram became stress strain diagram. But my dear, this engineering word is very important here. This engineering word have a meaning that is false. Why it is false? Because my dear, when you are going to take this stress P upon A naught, you very well knows when you will be applying the forces, area will be reducing, length will be increasing throughout. But my dear, you are taking the stress to be P but a original area of cross section. It is like on the first of every month you are going to get some salary or you can say pocket money from our parents. So our parents are sending some pocket money on the first of the month. Then my dear, after 15 days, obviously we will be having lesser amount of money because we would have spent some amount. But if after 15 days also we feel that we are having the same amount which was sent by our parents, is it correct? No, it is not correct. Okay, dear, I feel Knox Smith, dear, what you have asked about strain aging, that we are going to discuss in material science. So for that you need to wait slightly, but yes, I will be telling you about strain, some basic idea I will be giving you about the work hardening and on, but the complete discussion on strain aging will be there in the material science. So you need to wait for that. But yes, today you are going to know a number of things related to stress strain diagram which you previously was not having. Yes, Krishan Kumar, the next class will be on the Mohr circle only. Is it fine? Yes. So whatever you have asking, this kind of cortical atmosphere, all these things are going to come under material science when you will be discussing why mild steel is having 2 yield point. Then that discussion will be having these kind of answers, guys. Hope you got Knox Smith. So don't worry, in material science I am going to discuss both the things you have asked. Okay, so don't worry. And I really liked your questions. They are wonderful questions. Okay, my dear. So when we are talking about this, load was replaced by engineering stress, delta was replaced by engineering strain. So when it becomes stress strain diagram, my dear, now whatever be the area, whatever be the length, it is independent of that. My dear, I would like to tell you that this is a standard experiment. This is a standard experiment. Yes. Okay. So my dear, this is a standard experiment where we are going to get 19 elastic properties. And I would also like to add that whenever you are going to perform the tension test on universal testing machine, then my dear, all the tests are performed under the guidelines of ASTM. ASTM is saying American Society of Testing and Materials. It is American Society of Testing and Materials. And my dear, according to ASTM, there are some guidelines that length to the diameter ratio will be 4. My dear, diameter is generally half inches and length is going to be generally 2 inches. These are the consideration of American Society of Testing and Materials. Is it fine? Yes. Yes, dear. In this crash course, we are going to discuss a lot of things. So once again, I am showing you this. This is the setup detail and this is the specimen. Now we are going to start, my dear. When we are going to perform the test for the mild steel, we are going to have this type of curve. So this type of curve you will be getting when you will be performing the tension test onto the universal testing machine. Then my dear, if you see this stress strain diagram, you can see here it is engineering stress, here it is engineering strain. And my dear, this is for mild steel, and I would like to tell you that this is the first point which we are going to get, and this point is said to be the proportional limit. My dear, this point is said to be the proportional limit. This is something about which the students are aware of. So when we are talking about the proportional limit, this is the point up to which material obeys Hooke's law. So my dear, this is the point up to which material obeys Hooke's law. And when I am saying that material is going to obey Hooke's law, it means stress is directly proportional to strain. And some people may be asking one thing, sir, when you are writing stress is directly proportional to strain to the power 1, obviously it states that the diagram is going to be the straight line diagram. And it is also very much obvious that when you will be applying the proportionality constant, it is going to be E times of epsilon, and we will be getting E is nothing but sigma upon epsilon, which is nothing but the tangent theta. That is, my dear, nothing but the slope of this curve. And my dear, if you can see, the slope of this curve is very much near to 90, because this curve is very much near to this stress axis, y axis. So my dear, this slope is very, very big. So Young's modulus for mild steel is having very large value, one thing. But my dear, one question may be there, that every material follows Hooke's law. No, my dear, every material do not follows Hooke's law. So my dear, there are some material which do not follow Hooke's law, like grey cast iron. So when we are talking about the materials which do not follow Hooke's law, then my dear, for those materials, obviously when you will be making stress strain diagram, it is going to be a curvature. Curvature means it is not going to be a straight line, which means sigma is directly proportional to epsilon to the power n, where n is not equals to 1. So for such case, my dear, Young's modulus is not defined. Third, that machine I cannot be able to understand. Don't worry, Asutosh, that machine you need not to understand here. Don't worry. मशीन को समझना जरूरी है भी नहीं, ठीक है, जरूरी है इस डायग्राम को समझना, क्योंकि यू आर गोइंग टू गिव थ्योरी एग्जाम, नॉट प्रैक्टिकल इन गेट. Okay, so my dear, when the curve is non-linear, then my dear, Young's modulus is not defined in the way we have defined here. For such kind of curve, we are going to define, my dear, we are going to define tangent modulus. We are going to define tangent modulus and secant modulus. So we are going to define tangent modulus and secant modulus. Like if you are going to make the tangent at any point, it will give you the slope of this line will give you tangent modulus. If you are going to join this and this point, then slope of this line will be giving you secant modulus. You guys may be interested to know about these modulus, but they are not important for us, because we need to study only those material in strength of material which are going to follow the Hooke's law. Is it fine? Manas, plain truss already I have taught on this channel only. You can search the video, and don't worry, if you want, you can just message in the comment section and you will be getting those videos of trusses. I have taught complete truss with method of joint, method of truss, method of section on this channel only. So you can see that. So my dear, proportional limit is very well explained. My dear, then the one more point is coming, B point, that is known as elastic limit. So my dear, when we are talking about the elastic limit, it is that point up to which material obeys elasticity. तो माय डियर अब तक हुक्स लॉ की बात हो रही थी, अब बात हो रही है दैट मटेरियल विल ओबे द इलास्टिसिटी, मटेरियल विल शो द इलास्टिसिटी. So my dear, what is elasticity? If I apply some force onto this workpiece, and after applying some force, obviously there should be some deformation, and after some deformation, if I leave it, the material will regain its shape and size. That is something known as elasticity. Okay, is it fine? Dear Nilesh, when you are going to talk about that, then my dear, we will be defining some topic known as proof stress. Proof stress is acting like yield strength. So you will be joining the origin with the proof stress, and then you will be getting the secant. Okay, so that is not required for you, otherwise I would have given you all these things. Okay, so my dear, when we are talking about elastic limit, yes, very good guys, many of you are giving the answer, very good Jinil. So my dear, when we are talking about the elastic limit, it is the point up to which material obeys elasticity. It simply means that if you are going to load up to this point, after unloading you will be reaching to the original point, my dear, without any plastic deformation. So my dear, you can reach to the original point without any plastic deformation if you are going to unload after the elastic limit. Okay, yes. So my dear, let us move further. So after this elastic limit, if you further going to load the component, my dear, you will be getting a point known as upper yield point. My dear, now about this point, many misconceptions are there. So this is C dash, if we are going to see this region in a zoomed way, then this, my dear, this point is said to be upper yield point. So my dear, to understand the yield point, we must know that what is Sudarshan. If you want to see the schedule of this, it is already given in the description box, you can see that. Okay, so my dear, when we are talking about the upper yield point, to know about that you must know the definition of yielding. So my dear, yield means perfectly plastic behavior. Yield means perfectly plastic behavior. Now what do you mean by perfectly plastic behavior? If you are going to make a stress strain diagram, then my dear, if strain is increasing at constant value of stress, like this, at constant value of stress, if strain is increasing, then my dear, this is known as yielding. So my dear, this is the definition of yielding. And if you see properly, after this lower yield point, which is this one, C is the lower yield point, C dash is upper. After this lower yield point, almost it is following the yield, almost it is following the perfectly plastic behavior or yielding. So my dear, that is why this lower yield point is considered the actual yield point. But when we are talking about upper yield point, it is not at all the actual yield point. One more point I would like to add here, guys, when we are talking about the lower yield point, my dear, upper yield point and lower yield point, upper yield point is going to change when you change the specimen. Upper yield point is going to change if you are going to change the working conditions. Upper yield point is going to change if you are going to change the machine. So whenever you will be changing something, then my dear, upper yield point is going to change. So upper yield point cannot give you the property. Lower yield point will be giving you the property, and the best thing about the lower yield point, my dear, is that lower yield point is going to follow, after that material is going to follow the definition of yielding. So lower yield point is the actual yield point. Actually upper yield point एक तरह का धोखा है जो सिर्फ लो कार्बन स्टील में मिलता है. इस दुनिया में लो कार्बन स्टील के सिवा ऐसा कोई मटेरियल है ही नहीं जो दो yield point शो करे. There is no material in this universe except mild steel which can show two yield point. There are some material which do not show even a single yield point. So my dear, this is the only material which shows two yield point. And yes, the answer for these things you are going to have in material science for sure. There we will be discussing about that. Okay, and when we are talking about, yes, stress is equals to strength, no dear, you will be saying yield strength to be the stress corresponding to the lower yield point. So lower yield point will give you the yield strength, not upper yield point, because lower is the original one, upper one is not the original one. So guys, please tell me now you got it or not. Yes, Sunil, you got it now? Little monkey, actually when we are talking about the grey cast iron, actually due to presence of the graphite flakes, it always shows different behavior than the other material. Like in casting, you know, in the second phase it shows opposite behavior. When you go for metal cutting, due to graphite flakes, my dear, we cannot use any lubricant for that. We are going to use compressed air as a lubricant. Okay, dear, video will be available, don't worry. Okay guys, so after this lower yield point, my dear, you can see the curve is going to go up and you will be getting one point that is known as ultimate point. So my dear, now this is what mathematically I have given you, what is going on and what is not going on. Now I will be telling you something related to physics. My dear, what is going on exactly? Up to elastic limit, why the material is going to come back to the original state after removal of load? Why it is going to happen? So my dear, when you are going to load some material, what is going on? Let us say there are two atoms. They are going to go slightly far away from each other when you are going to apply the forces. And my dear, when they are going to go far away, you know, in two atoms there are two nucleus which are positively charged. There are electrons which are negatively charged. So my dear, positively charged nucleus will be having repulsion between each other. Electrons will repel each other. But nucleus of one atom will be attracting electron of other, and nucleus of second will be attracting electron of first. So my dear, there are some attraction and some repulsion forces will be there. There are some attractive and some repulsive forces will be there. So my dear, whenever you are going to take two atoms away from each other, my dear, then what happens? The attractive forces are increasing, repulsive forces are reducing. When two atoms are coming closer to each other, attraction is reduced and repulsion is increased. This is how the things are going on. So my dear, when you are going to take two atoms away from each other, after removal of load, their attraction will make themselves again at the original position. That is due to elasticity. But after elastic limit, my dear, what is going to happen? Actually, the bonds get broken. So bond टूटने लगते हैं elastic limit के बाद, and once the bond get broken, my dear, atoms are going to start moving, and once atoms are going to lose their position, they will never come back because some other atom may have taken their position. So when you are continuously applying the forces after breaking of bond, these atoms will start moving under the action of the force. So my dear, such groups of atoms, like 3 atoms are moving like this, 5 atoms are moving like this, 7 atoms are moving like this, 8 atoms are moving like this. So these groups of atoms are said to be dislocation because this is the group of atoms which have left its own position. So my dear, when a group of atoms are going to move under the action of force, that dislocation movement is said to be slip. So the group of atoms which have left their position is said to be dislocation. The movement of dislocation is said to be slip. The movement of dislocation is said to be slip. Okay guys, so my dear, now we are talking about dislocation movement, which is slip. So my dear, up to elastic limit there is no dislocation movement because up to elastic limit bonds are not broken. After that the bonds are broken, so atoms and groups of atoms are going to move. Is it fine? So when groups of atoms are moving, my dear, they are moving under the action of force. It is like when you are going to apply some force, when you are going to start the vehicle, initially you need to apply more torque. Once the car started, you are going to shift the gears, because after that, you know, we can run the car with lower torques. Why? क्योंकि एक बार चीज शुरू हो गई तो उतना टॉर्क नहीं लगाना पड़ता. Once something is started, we need not to apply more forces. So that's what I want to say, that my dear, once the atom's movement is started, during yielding you need not to apply more forces. That's why this reduction of force is there, this reduction of stress is there. But my dear, once you are going to cross this point, after that what is going on? These dislocations are coming in the path of each other. So when these dislocations will be coming in the path of each other, my dear, the movement of dislocation is going to become very, very difficult. So now, my dear, the movement of dislocation is going to become very, very difficult because they are coming in the path of each other. So you need to apply more and more forces for their motion. Is it fine? Sir, why and what is the use of stress strain diagram considered as important? Why, sir? Dear, actually, when we are going to talk about stress strain diagram, it is giving you elastic properties. Young's modulus you are getting from here, yield strength you are getting from here, ultimate strength you are getting from here. 19 elastic properties you are going to get from this diagram. And all these elastic properties are going to be helped in the designing It is going to help in metal forming, in metal cutting, in production, in machine design. So everywhere these properties are required, which you are going to get from this diagram. So my dear, that is why the strength of the material is going to increase up to ultimate point. Then my dear, at ultimate point, actually the crack gets started. Crack gets started. So एक बार crack आने के बाद, after that the crack is going to propagate, and due to the propagation of crack, my dear, the strength of material is going to reduce, and my dear, at this point the body is going to break into parts, and my dear, this is said to be fracture point. So my dear, this is said to be the fracture point. So my dear, plastic deformation start after elastic limit, and fracture takes place at this point. And if you divide the regions, my dear, then up to elastic limit, this region is said to be elastic region, and up to this point, this is said to be the yielding region. And my dear, this is said to be the strain hardening region, because here the material strength is increasing because of the strain coming in the material, and this region is said to be the necking region. Now my dear, the questions are coming from this, that in strain hardening region you can see this is a curvature. So my dear, this curvature, in this curvature, it is going to follow a law known as power law in strain hardening. Sigma is directly proportional to epsilon to the power n, where n lies between 0 to 1 for mild steel. You can see this curve is following which nature? This is the curve of root x, and this is the curve of x square. So you can see, my dear, in power law of strain hardening, it is following root x type of nature. So if it is going to follow root x type of nature, if you know sigma is directly proportional to epsilon to the power 0.5, then my dear, if strain is going to become 9 times, you know stress will become how many times? Stress will become how many times, guys, when strain is becoming 9 times? Yes, work hardening region. Yes, very good, Sudarshan. And that region is also known as necking region or strain softening region. Very good, guys. Okay, yes, for sure. So my dear, if it is becoming 9 times, how many times the stress will become for this relation? If strain will become 9 times, how many times the stress will become? Can anybody answer this? Dear, square root of 9 is not 4.5. Square root of 9 is, square root of 9 is, कहां खोयो भैया? If stress is directly proportional to epsilon का square root, when strain will become 9 times, how many times the stress will become? हद हो गई यार, 9 का स्क्वायर रूट क्या होता है? 3 नहीं होता क्या है? स्क्वायर रूट ऑफ 9 is 3 ना, so it will become 3 times. So my dear, आप देख सकते हो, जब स्ट्रेन 9 गुना हो गई तो स्ट्रेस 3 गुना हुई. तो आउट ऑफ स्ट्रेस एंड स्ट्रेन विच इज इंक्रीजिंग एट मोर रेट, स्ट्रेन और स्ट्रेस में से कौन ज्यादा रेट पर बढ़ रहा है? वेरी गुड परविंदर, वेरी गुड चंद्रशेखर, वेरी गुड जीवन. तो स्ट्रेस और स्ट्रेन में से कौन ज्यादा रेट पे बढ़ रहा है? विच इज इंक्रीजिंग एट फास्टर रेट, विच इज इंक्रीजिंग एट फास्टर रेट, स्ट्रेन और स्ट्रेस. In strain hardening region, which is increasing at faster rate, strain or stress, guys? Which is increasing at faster rate, strain or stress? Yes, very good, Asutosh. So strain is increasing at faster rate. Strain is increasing at faster rate. तो strain ज्यादा rate से बढ़ेगा. So my dear, this question have already been asked in engineering services, that in strain hardening region which is going to increase with more rate. So strain is going to increase at faster rate. Okay guys, fine. So this is about stress strain diagram. Now I want to ask one question from you. This is the last question from this topic, then we will be going to the next diagram. So my dear, when we are talking about this diagram, I want to ask you that how the machine comes to know when we are going to load like that. How the machine comes to know that up to this point the load should be increased. After that the load has to be decreased. After that the load has to be increased. And after that the load has to be decreased. How do machine knows that when to increase and when to decrease the load? Can anybody answer? The student who have joined the GATE Champion study plan, I have discussed this thing. Please let us see how many of you get answer for this. Yes guys. Yes guys. Why miles is shown both upper and dear, I already told you that we will be discussing in material science कि milestone क्यों दो yield point show करता है. Can anybody answer? Yes, times of cinema. So my dear, how it comes to know? Actually, when this material is going to be loaded, okay. So my dear, when you are going to give the load, you don't know, machine do not know, because you are working on the machine. Either machine will be working on some pattern, like you are making the pattern that load is always increasing, or load is increasing with some of the curvature, or load is decreasing with some of the curvature. Actually, when the machine is working, machine is not working to increase or decrease the load. Machine is working to give the constant rate of deformation. Machine is working like it has to deform the material 1 mm per second, 1 mm per minute, 2 mm per second. Like machine is working like that. So when the machine is working on the strain rate, so whenever the material will be showing more resistance, machine apply more force. Whenever the material is showing low resistance, material will be showing the low resistance, machine will be applying the less number of loads. So this is how we can define it, guys. So this is the first diagram, and now we are moving to the actual stress strain diagram and engineering stress strain diagram. So my dear, when we are talking about the actual stress strain diagrams, so I would like to tell you one thing. Now we are going to discuss about true stress versus true strain. True stress versus true strain. We are going to discuss about true stress versus true strain. So when we are going to discuss about true stress and true strain, my dear, okay, Prajwal is asking, will this crash course with our hard work help? Definitely dear, definitely Prajwal. For that it is only. Very good guys. Very good Sudarshan. Elastoplastic region we consider as elastic region. Why sir? Elastoplastic region we considered as elastic. No dear, we have not considered like elastic. Up to elastic limit I said elastic. Okay. So my dear, now we are talking about true stress versus true strain. So when you are going to apply some load onto this material, you know initially the area is nothing but A naught. Initially the area is A naught. So my dear, engineering stress can be defined as force but a original area of cross section. So you know when you will be loading, with that time the area will be reducing and length will be increasing. So let us say initially length was L naught, now length is Li and area is Ai. After some time area will reduce more, length will increase more. So my dear, you will be having the final area to be AF. So my dear, if you want to write down the true stress is defined as load but a instantaneous area of cross section. A naught is the area at time is equals to 0. Ai is the area at time is equals to t. When the time will change, the area will change. So my dear, the point is, you need to write the true stress as load but instantaneous area, but instantaneous area cannot be calculated, because to measure this area we need to stop the testing, and once you are going to stop the test, my dear, then definitely elastic deformation will go, because elasticity is defined after removal of load. Elastic deformation do not remain with the material. So my dear, when this is the case, so obviously Ai is not a measurable quantity, we cannot measure it. हम इसको measure नहीं कर सकते. So we do not know this. So my dear, then we can write true stress to be equals to P but a original area into original area but a instantaneous area. We can write it in this way. And you know, this is the definition of engineering stress. So sigma T is equals to engineering stress into A naught by Ai. Then my dear, obviously Ai is not a measurable quantity, so we need to go with some of the assumptions. Yes, this is the first lecture, Harsh. This is the first lecture. So my dear, now we will be moving for the assumption, and my dear, we are going to make one assumption. That assumption is that initial volume is equals to final volume. Yes, this is not true because volume is going to change. That's why volumetric strain is defined. So how volume can be same? So volume is variable, no doubt about that. But my dear, still if you are assuming that, you can write original area, original length, instantaneous area, instantaneous length. So my dear, that is why you can say A naught by AI is equals to Li by L naught. You know, Li is nothing but L naught plus delta, because some length have been increased, divided by L naught. So you can write it as 1 plus delta upon L naught, and this is nothing but the engineering strain. So my dear, the expressions for true stress are coming out to be engineering stress into 1 plus epsilon E. Now my dear, I want to ask you one question, that out of true stress and engineering stress, which one is bigger? Out of engineering stress and true stress, which one is bigger? Engineering stress और true stress में से बड़ा कौन है? Out of engineering and true stress, which one is bigger? Pradyuman, actually this is our assumption, because there is no material which is perfectly incompressible, because in solid material we find out volumetric strain. So volumetric strain means volume is changing, but we are assuming it to be constant because we don't have any other way to go. Can you tell me which one is bigger? True stress or engineering stress? Okay, Asutosh Mishra is saying true. Pradyuman, Akash are saying true. So my dear, I would like to correct you here. My dear, if tension is there, then no doubt true stress is going to be more than engineering stress. But let us say if we would have compression, in case of compression, this would be L naught minus delta. It would be minus here, because then the length would be decreasing and area would be increasing. So here also we will get minus. So my dear, if compression is there, then true stress is less than the engineering stress. So my dear, always we cannot say that true stress is more. And I would like to tell you, my dear, this was question asked in GATE 2012, that the relation between true stress and engineering stress. Similarly, my dear, we can derive true strain to be equals to ln 1 plus engineering strain. This is the relation between true strain and engineering strain. They are very, very important relation for the GATE exam. Hope you guys are getting it. Is it fine? Yes. So guys, let us move further. Let us move further. Let us move further. So my dear, you can see the actual means true stress strain diagram and engineering stress strain diagram. So true stress strain diagram will be going up in case of tension. In case of tension, this curve is going to be up. And my dear, when you will be having the compression, then actual curve will be below the engineering curve. So this is the case of compression. This is the case of compression. Is it fine? So whatever I have given you, you can see actual curve for compression will be below the engineering curve, and actual curve for tension will be above the engineering curve. So this is the entire curve. So my dear, you can say if original curve is like this, then this curve is for true stress tension, this is for true stress compression, this is for engineering stress. Is it fine? Okay guys, so let's move further. Let's move further guys. Okay guys. Okay. So let us move further. How can we identify them? Dear, you can identify only from the engineering curve. When this is engineering curve, then obviously below this will be actual curve for compression, above this will be actual curve for tension. Nobody is going to ask you the value, so don't worry about that. Okay, कोई आपसे value नहीं पूछेगा. Kiran, I would like to tell you that when you are talking about the engineering stress, it is load but a original area of cross section. You know, whenever you will be loading this element, the area will be continuously decreasing and length will be increasing. So area will be decreasing and length will be increasing. So my dear, every time when area is increased, so true stress should be load but a instantaneous area. So true stress is nothing but load but a instantaneous area. Engineering stress is load but a original area. You can say this is true stress, the actual value of stress, and this is nothing but the theoretical value of stress. Theoretical value is false value. But the point is, my dear, this we cannot calculate. Sorry, we cannot measure. So that is why we need to play with this. So that is why we are moving with engineering stresses. Now is it fine? Now is it fine, guys? Okay, let us move further. Let us move further. Yes, we are talking about mild steel only. So guys, now this is the curve. This is the curve where you can say this is low carbon steel. You can say this is medium carbon steel. This is high carbon steel. So my dear, if you can see, this is the all types of steel curves are together. So when we are going to make all the steels together, you can see for all these three curves, the slope is going to be same. The slope is going to be same. So my dear, you know, if slope is going to be same, means Young's modulus of low carbon steel is equals to Young's modulus of medium carbon steel is equals to Young's modulus of high carbon steel. So we can say one thing, that my dear, Young's modulus is same for all the grades of steel. For all the grades of steel. So my dear, steel के सभी grades के लिए Young's modulus की value same होती है. This is a very important point. And guys, if you see in this low carbon steel, we will be having this region to be elastic and this region to be plastic. Why? Because after elastic limit we will be having the permanent deformation. And my dear, if you are going for the medium carbon steel, for medium carbon steel you can say up to this point we will be having the elastic, and after that we are having the plastic. So my dear, similarly if you are going to see for the high carbon steel, this region is going to be the elastic and this region is going to be the plastic. So can you tell me that if we are going for the elastic region, out of low carbon steel, medium carbon steel and high carbon steel, which steel is showing more elastic region? Yes, very good, Parvinder. So can you tell me guys, out of low carbon steel, medium carbon steel, low carbon steel, medium carbon steel, high carbon steel, which is having the highest elastic region? कौन से मटेरियल का? डियर, माइल्ड स्टील और कास्ट आयरन मैकेनिकल इंजीनियरिंग में 98% एप्लीकेशन को कवर करते हैं, इसीलिए आपसे सब कुछ पूछा जाता है माइल्ड स्टील और कास्ट आयरन के लिए, और उसमें भी माइल्ड स्टील मैकेनिकल वालों के लिए ज्यादा इंपॉर्टेंट है. सो माय डियर, वेरी गुड. फॉर इलास्टिक रीजन, फॉर हाई कार्बन स्टील इज मोर देन मीडियम कार्बन स्टील इज मोर देन लो कार्बन स्टील. सो माय डियर, हाई कार्बन स्टील के लिए इलास्टिक रीजन सबसे बड़ा है. एंड व्हेन वी आर टॉकिंग अबाउट द प्लास्टिक रीजन, so my dear, when we are talking about the plastic region, for low carbon steel, my dear, plastic region is bigger than for medium carbon steel, is bigger than for high carbon steel. So my dear, plastic region indicates ductility and elastic region indicates elasticity. So my dear, from here you can say that low carbon steel is more ductile and high carbon steel is more elastic. तो लो कार्बन स्टील ज्यादा डक्टाइल होता है और हाई कार्बन स्टील ज्यादा इलास्टिक होता है. हाउ मेनी ऑफ यू गॉट दैट गाइस? यस, थैंक्स गाइस फॉर योर वंडरफुल कमेंट्स एंड वेरी गुड. तो गाइस, आर यू गेटिंग इट? सभी को समझ में आ रहा है? यस. सो गाइस, लो कार्बन स्टील इज गोइंग टू बी मोर डक्टाइल high carbon steel is going to be more elastic. Even cast iron is more elastic than high carbon steel. So my dear, mild steel, low carbon steel को mild क्यों बोलते हैं, ये क्वेश्चन का आंसर मैं कई बार कर चुका हूं. You guys know one thing, that whenever you are going for the heat treatment to improve the property, then my dear, you know low carbon steel की जब हम बात करते हैं तो low carbon steel क्या नहीं करता? Low carbon steel क्या नहीं करता? It do not respond to the heat treatment. इसकी प्रॉपर्टीज इंप्रूव नहीं होती हीट ट्रीटमेंट करने पर. एंड दैट इज द रीजन माय डियर लो कार्बन स्टील वाज गिवन द नेम ऑफ माइल्ड स्टील, बिकॉज इट्स रिस्पॉन्स इज माइल्ड. माय डियर एल्यूमिनियम, मैग्नीशियम एंड देयर एलॉयज, ये ऐसे मटेरियल हैं जो एक भी यील्ड पॉइंट शो नहीं करते. इज इट फाइन? एक्चुअल कर्व आप किसी की भी बनाओगे तो वो इसी नेचर को फॉलो करेगी, वैल्यू कम ज्यादा हो सकती है. इज इट फाइन? यस, वेरी गुड परविंदर, वेरी गुड गाइस टू ऑल ऑफ यू. चलिए गाइस, तो बढ़ते हैं आगे नेक्स्ट कर्व की तरफ. बाय डियर, नाउ वी आर गोइंग फॉर द एक्चुअल मटेरियल्स कर्व्स. दिस इज द इंजीनियरिंग मटेरियल कर्व्स. आप देख सकते हो, यू कैन सी फ्रॉम दिस कर्व, दिस इज द कर्व फॉर माइल्ड स्टील, दिस इज द कर्व फॉर कास्ट आयरन, दिस इज द कर्व फॉर एल्यूमिनियम. And my dear, this is the curve for wood, this is the curve for rubber. If you see all these curve, my dear, the first observation is the slope of low carbon steel is highest, then the slope of cast iron, and then the slope of aluminium. So you can see, my dear, Young's modulus of mild steel is found to be 2 times of Young's modulus of cast iron, and it is found to be 3 times of modulus of aluminium. So my dear, this is the relation between mild steel, cast iron and aluminium, and that is why elastic region is highest for aluminium, good for cast iron, minimum for mild steel. And if you see the second thing, if you see the cast iron curve is going so much up here, whereas cast iron curve is coming this level here. So when you see properly, here it is less than 40, here it is more than 40. It means yield strength in compression for cast iron is more than yield strength in tension for cast iron. My dear, not only this, I would like to tell you here a very, very important point. If you go for any material, yes, very good Akash, very good Pradyumn, yes, Naga Smith. So my dear, when we are talking about any material, if the material is going to be brittle material fails under tension, so their ultimate strength in compression is always more than ultimate strength of shear, is always more than ultimate strength of tension. But my dear, if you are going to talk about the ductile material, then ductile materials are also good in compression only, then that of tensile, then that of shear. So I would like to say that ductile material fail in shear, brittle material fail in tension. So my dear, whether it is ductile or it is brittle material, every material is going to perform well in compression. Every material is going to be the best in the compression. Is it fine or not? Is it fine or not? Every material is found to be good under compression, guys. इस दुनिया के सभी मटेरियल कंप्रेशन में अच्छे होते हैं. वेरी गुड परविंदर, बहुत ही बढ़िया. ओके गाइस, सो लेट अस मूव टू द नेक्स्ट डायग्राम. One by one we are going to discuss about all the diagrams. My dear, this is about stress relaxation. Sir, cast iron is more elastic than, yes, cast iron is more elastic than mild steel for sure, no doubt about that. Okay, no doubt about that. Is it fine? Dear, elasticity, ductility and brittleness, all three are different things. Yes, cast iron is brittle, no doubt about that, but cast iron is more elastic as well. So my dear, this is stress relaxation. Actually, there is a phenomena creep in which elastic deformation is going to convert into plastic deformation after some time. Whenever you are going to apply some elastic deformation onto this body, after some time elastic deformation will be converting into the plastic deformation. It means if you are having a fan, let us say there is a fan rod on which you are having a fan. Okay, this is, we are talking about ceiling fan. So my dear, due to the weight of this fan, this rod may increase in length, but initially this deformation will be elastic, but after some time this elastic deformation will be converting into plastic deformation. This is said to be creep. So my dear, similarly when you are having some high tension cables, so those high tension cables are initially have some stress value. So initially we are going to load up to elastic limit, it is having some stress value. But when it is loaded for the longer times, my dear, what happened is, my dear, their elastic deformation is getting converted into plastic deformation. So you see after some time the wires get sag. लटक जाती है कुछ दिनों के बाद वो wires. So my dear, elastic deformation gets converted into plastic, जिसके कारण वो लटक जाती है, and stress value are getting reduced and become constant. And this phenomena is said to be stress relaxation. Are you clear about this phenomena or not, guys? Please tell me that. Are we clear about this phenomena or not? Please tell me that. Yes or no? Yes or no? Fine. Okay, guys. So my dear, now we are moving to the properties slides. Okay. So my dear, this is loading unloading diagram. When we are talking about loading unloading diagram, guys, I would be teaching you this with this example. Let us say we are having this body. And you know, when we are going to start loading this body, I am going to bend it. So for bending it, I am applying some force, applying some force, applying some force, applying some force. Up to some time it will be elastic deformation. After some time the deformation will become plastic. I loaded it, I loaded it, I loaded it, I didn't stop, I loaded it, I loaded it, I didn't stop. And after loading to that much extent, let us say I am removing the load. So when I am removing the load, you can see this is coming back by this amount. So my dear, when I was loading, I started from here and I loaded first elastic and then plastic, and after removal of load, you know, elastic deformation vanishes. So it becomes at this position. It means now it is left with this permanent deformation. So when I have loaded initially elastic, then plastic, after removal of load, plastic is getting removed, elastic is getting removed, plastic is with the body. So my dear, this is something known as the concept of elastic recovery. That elastic deformation is recovered from the body during unloading. Is it fine? नहीं भाई, देखो डियर, वो डिपेंड करता है आपने किस लिए स्ट्रेस किया हुआ है. वहां पर आपने जब तारों को लटकाया था तो फेल की बात हम तब करेंगे जब वो फंक्शन प्रॉपरली नहीं करेगा. ओके, फेल तो वो हो गया प्लास्टिकली, बट वो फंक्शन प्रॉपरली कर रहा है. मैकेनिकली आप उसको फेल बोल सकते हो, इलेक्ट्रिकली वो फेल नहीं है. ठीक है? इज इट फाइन नीलेश? So my dear, when we are talking about this loading unloading diagram, my dear, let us say this is elastic limit. If you are going to load up to elastic limit and going to unload, it will be coming back. But my dear, if you are going to load it after elastic limit, then if you are thinking of unloading the material, then unloading will not result in coming back. Now unloading will be following this curve. So unloading will be parallel to this curve. So my dear, this theta will be followed by this theta. Both the theta will be same. So my dear, when you are going to load, then my dear, this is elastic deformation and this is plastic deformation. And during unloading, my dear, during unloading, my dear, this is elastic and this is remained with the material permanently. This is plastic. So my dear, this phenomena is said to be elastic recovery. Guys, it is a theoretical topic, but it is very, very important. This is said to be elastic recovery. And my dear, yes, very good. So it is said to be elastic recovery. And my dear, in case of bending, it is also known as spring back effect. It is also known as spring back effect. If you are going to compress a spring, spring will come back. Okay, so this is loading unloading diagram. Always remember, this angle and this angle will be same. Is it fine, guys? Okay, now my dear, I know you are very much aware about the properties. You are very much aware about the properties like hardness, elasticity, ductility. So I'm not going much into that, but I'm going into the properties which are related to stress strain diagram. Like we are having resilience. Okay. Okay guys, so before going into that, let us discuss about strain energy. My dear, whenever you are going to apply some force onto this member is going to deform by some amount, and let us say this deformation is delta. If you are applying some force P, you know my dear, work done is defined as F dot ds. As force and displacement are in same direction, we can also write F ds cos theta. As the angle is 0, we can also write it as F ds. You know my dear, the loading is gradually applied loading in strength of material. We assume it like that. So due to that gradually applied loading, you know, if this is 0, this is P. Due to linear variation, we will be taking the F to be average. So that work done is nothing but energy stored in the body in the form of strain energy. It is also written as F average into delta. So it is given as half into P into delta, because F average is 0 plus P by 2. Is it fine guys? So I am going slightly faster now. So my dear, you know, when we are going to make a stress strain diagram, let us say I am going to make a stress strain diagram. First of all, load deformation diagram. If this is the load deformation diagram, you know, load deformation diagram and stress strain diagram are coming same only. So my dear, if this is the elastic limit, so the area under this curve is said to be resilience, and my dear, the area up to this point, fracture point, यहां तक के एरिया को क्या बोलते हैं? It is said to be toughness. And my dear, resilience is defined as half into load at elastic limit into deformation at elastic limit. So energy stored in the body up to elastic limit is said to be resilience. My dear, up to elastic limit is resilience, and the maximum value of resilience is said to be the proof resilience. Please tell me how many persons, सभी लोगों को समझ में आ गया कि नहीं? Everybody got it or not? It means if we are going to have this as a diagram, and my dear, if we are going to have this point as the elastic limit, so area up to this point is resilience, area up to this point is resilience, but area up to this point is resilience, which is maximum, so it is said to be proof resilience. We are short of time guys, because you know there is a much detail on stress strain diagram, but I feel the time is less. So this is something said to be resilience, proof resilience and toughness. And my dear, same we can define in case of stress strain diagram. If we are having the stress strain diagram, then my dear, the area up to elastic limit is said to be modulus of resilience, and the area up to fracture point is said to be, guys, क्या बोलेंगे उसको? That is modulus of toughness. Is it fine guys? थोड़ा सा फास्ट जा रहा हूं, समझ आ रहा है कि नहीं? क्योंकि मुझे लगता है ये सारी चीजें आपने याद की हुई हैं. Proof resilience, very good dear. So modulus of resilience is nothing but proof resilience per unit volume. कैसे पता लगा? Because you know strain energy can be written as half into P into delta. We can also write it as half into P but a area into delta but a length into volume. You know A into L is the volume. So we can write it as strain energy per unit volume is equals to half into stress into strain. This is how we can define. So like P into delta is strain energy, sigma into epsilon is nothing but strain energy per unit volume. So guys, this is slightly quickly I am going because time is less. Now I will be showing you some questions. अब कुछ questions दिखाऊंगा मैं आपको guys. We will see some question. This loading unloading we have seen. Yes. Okay, fine. Okay, this is the first question in front of you guys. इससे भी पहले we will be solving next question. This question. The stress strain behavior of a material is shown in the figure. Its resilience and toughness in Newton meter, which is joule per meter cube. So joule means energy per unit volume. They are asking about strain energy per unit volume. So they are asking about modulus of resilience and modulus of toughness. So you can see red area will give you modulus of resilience because it is stress strain diagram. It is not load deformation diagram. So area under stress strain diagram will give you modulus of resilience. Area under load deformation diagram will give you resilience. So my dear, now this area will be modulus of resilience, and if you see this blue plus red both areas together, then blue plus red both will give you modulus of toughness. If you will find out only one, you will get the answer because there are 4 options. By looking at one, you can answer it. Parvinder have answered it as C. Okay. So guys, if you have any doubt, please ask. In the last, I have gone very fast because time is very less. Topic was quite big. But don't worry. Next topic is going to be Mohr circle. There we will not have any issue because Mohr circle is going to be discussed in 1 hour very easily. Pradyumn is saying C. Very good. And guys, if you have any doubt, you can ask in the Telegram channel of mine. You can ask me personally by doing WhatsApp. Okay, like some questions Next Smith have asked, you can ask me in the group. I will be answering that. So guys, the answer for this is going to be C. Very good. All of you are correct. Because when you will be answering about the modulus of resilience, it will be half into 70 into 0.004. So it is going to be 14 into 10 to the power 4. Why? Because this is MPa. Okay. So you will be getting the answer 14 into 10 power 4. And my dear, only one option is having this. So obviously C will be the answer. So modulus of toughness will be coming out to be 90 into 10 to the power 4. Adding both the areas, we will get this. Wonderful guys. So what will be the answer to this question? Okay. These are the properties: ductility, brittleness, toughness and tenacity. Tenacity means high tensile strength. High tensile strength. This is said to be tenacity. What will be the answer for this one, guys? So kindly like and share the session, guys. I try to give you the best, but the time is less, so definitely I skip the easier definitions only. So failure without warning, drawn permanently over great changes of shape without rupture, absorption of energy at high stress without rupture, high tensile strength. What is going to be the right answer? Without warning, the failure is given by which material? कौन से मटेरियल बिना वार्निंग के फेल हो जाते हैं? वार्निंग मतलब प्लास्टिक डिफॉर्मेशन. Which material do not show plastic deformation? Failure without warning is given by brittle materials. Very good, Pradyumna and Jeevan. Is it correct or wrong? Yes. High tensile strength is tenacity. C with 4. Yes. Drawn permanently over great changes of shape without rupture. Is it ductile? Yes. The answer will be D. आंसर विल बी डी. फाइन गाइस, तो आंसर डी होगा, बी नहीं. डियर, हर तरह की लोडिंग के लिए स्ट्रेन के साथ वेरिएशन इलास्टिक लिमिट तक लीनियर ही होते हैं. इलास्टिक लिमिट के बाद लीनियर नहीं होते हैं. ठीक है, इज इट फाइन नीलेश? तो इलास्टिक लिमिट तक लीनियर, इलास्टिक लिमिट के बाद नॉन लीनियर, क्योंकि पूरी सोम में आपकी अजम्पशन है दैट हुक्स लॉ इज वैलिड. तो अगर आप हुक्स लॉ को वैलिड मान रहे हो तो यू नीड टू कंसीडर दैट. वेरी गुड अब्दुल, वेरी गुड प्रद्युम्न, वेरी गुड जीवन. होप आपको अपनी गलती समझ आ गई होगी. टफनेस का मतलब है ज्यादा एनर्जी को ऑब्जॉर्ब करना, तो 3 इज गोइंग टू बी विद द डी. ओके, सो आंसर विल बी दिस. ओके, लीव करने से पहले लास्ट क्वेश्चन. ये एक नई तरह का क्वेश्चन है, मैं करा भी चुका हूं कई बार. आई हैव डन इट मेनी टाइम्स. सो माय डियर, दिस यू नीड टू फाइंड आउट द इलोंगेशन ऑफ ए बार made of this material, diameter 50 mm, length 2 meter, under axial tension 300 kilonewton. First of all, find out the value of stress. 300 into 10 power 3 divided by pi by 4, 50 का square. Find out this value. You will get this value to be somewhere here. So this is already known to you. We need to find out this deformation. And for this deformation, we already know the slope of this curve. We need to go for the similar triangles. Okay, and we can find out this. Let us say this is x, this is y. So you will be getting this sigma value for sure. This value will be known to you. So my dear, we can write y upon x is equals to 60 by 0.004. So you can find out y. Okay, y is already known to us. Sorry, we can find out x from here, and once we get x, x plus 0.002 is your answer. Let us see how many of you give the right answer for this. देखते हैं आप में से कितने लोग आंसर करते हैं सही. प्रद्युम्न is saying 8.47. 47 आएगा, 37 आएगा, चेक कर लेना एक बार. दिस इज द लास्ट क्वेश्चन गाइस. वेरी गुड परविंदर, वेरी गुड परविंदर. सो दैट इज गोइंग टू बी योर आंसर, एंड वाई यू कैन फाइंड आउट फ्रॉम दिस सिग्मा वैल्यू. ओके, बाकी लोग भी बताइए. वेरी गुड जीवन. So this is a new type of question guys. हाँ, 8.37 आएगा भैया. This is a misprint. Okay, so answer for this is going to be 8.37 mm. So guys, stress strain diagram एक बड़ा टॉपिक था. ठीक है, तो in 1 hour जो भी feasible था I have given you, but whatever I have given you, all the gate questions will be there from this. So guys, now I will invite you day after tomorrow, come join Mohar circle, and whatever you have learned today, on that I will share you some questions. Okay, you please try to solve those questions. Okay, nahi dear, actually 8.37 is the right answer, और यहाँ 8.37 ही आएगा, ये misprint है. ठीक है, okay. So guys, day after tomorrow we will be having the Mohar circle topic, and we must join that session, because that session will give you one question for sure, and that is a topic which we can very easily cover in 1 hour. So I will be showing, I will be doing some wonderful question on that day. So day after tomorrow will be the Mohar circle. Do share this session with others as well, so that they can also get the benefit. In case of any problem, any doubt, you can definitely ask me on Telegram, WhatsApp, mail, or in the doubt forum of BYJU. So goodbye guys for this session. Thanks for joining. PDF will be shared in the group right now.